Okay, so let's do one problem. Please turn to page 342, problem 7.30. So for this case, we are given a semicircular loop in free space, and then it has a radius of A, and then it carries current of I. So let's assume the I here flowing in positive phi directions. So now we are going to find the magnetic flux density, which is B. So we also know that the B can be related to the H by this equation, mu H, or also can put here mu R, mu naught H. And since this is a free space area, so mu R equal to 1, so finally gonna have here mu naught H only. Alright, so now we have to find the H that actually comes from this semicircular loop, right? So that's our H of interest. So since this is a finite structure, so we need to use a BSL to find the H that due to this semicircular loop. So let's do using BSL that the H actually equal to the I dl, because it's a loop, right, line current. So across the vector of R over 4 pi R squared, or you can even change to this form, I dl cross R vector over 4 pi R cube. Okay guys, so guys, this is our current element, right? We need to take a sample or current element from this semicircular loop. So let's say this is my sample or current element given as here I dl vector. Okay, so we also know that the dl here can be expressed in terms of this form, I a d phi in phi directions. Since the R is constant, so you can simply change become to A. So that's our current element expressions. Then we are going to find the R. The R vector actually just the R that pointing from current element to the point of interest. So that should be your R directions. R vector from element current to the point of interest. So the R here guys actually can be expressed as shown here, negative AR only, because we are going to find the H at the center of the loop, which is at the same Z plane. So now we only have the R component. So why negative? Because now this R vector radially inwards, okay? And why A? Because the R here is kept constant all the times, right? The only change only in phi, and the R remain constant. So this why I can just change R here become A. Okay, so let's proceed to find the H. The H. Now we have here I A d phi in phi directions cross, see the R vector, negative A R component over 4 pi A cube, right? Because this is our magnitude of the vector of R. So now vector R is minus A, so by right magnitude of vector R should be in A only. So now we have here A cube straight away. Now let's do cross product between the phi and R. The phi R here gonna have here supposed to be a negative Z, because based on the simple analysis we know that this is your Z, this is your R, this is your phi. So the R cross phi will have positive Z, the phi cross Z will have positive R, the Z cross R will have positive phi. But now we are going to find the phi cross R the other way around. which is from here. I want to find the phi cross r, so the output should be a negative. Right? Very well. So now let's proceed. Let's integrate the d phi now. Now I have to h here left. So the a times a got a squared. So I a squared, and then minus times minus got positive z. So now z directions over 4 pi a cube. Then integrate over d phi and limit from 0 to pi because semicircular, 0 to pi, and finally gonna have here the h is equal to z directions I over 4a ampere per meter, right? Because the a here square and left 1 only, so pi here with pi there only left 4. So now you can simply find the b from this z directions, mu naught I 4a, and now it has unit of Weber per meter or Tesla. Right guys, so this is the result, okay, for this problem. So please help yourself redo and understand the flow. Okay, thank you.